All right, so after that set of notes about how to use the measuring equipment, we're going to run you through some examples of real-life measuring equipment. We're going to measure the mass on a balance. We're going to measure some volumes using the graduated cylinders. We're going to measure the temperature of the room. We're going to look at some beakers, some flasks, some burettes, and a couple of ways to measure length or width.
Here we've got two burettes, a 50 mil and a 100 mil burette. If you remember when we introduced the equipment to you, Mr. Risner told you that the scaling on this is in the reverse. So at the top is 0, and at the bottom is the maximum amount that you can measure out of the burette. The way these are set up, it's to tell you how much has been dispensed, not how much is in the burette. So starting with the 50 mil burette here, what we want to do is look at the smallest scaling that we can see. So we can clearly see that there's larger hash marks on here that indicate 1 mil increments. And then there are 10 hash marks in between, or 10 divisions between, let's say, 24 and 25. So that tells you that this is scaled by 0.1 milliliters. So that means that you can know with certainty at least to the nearest tenth of a mil. And we always go one additional digit that is uncertain or that you estimate, and you must figure out what that is. So if you take a look at this 50 mil marking on here, we can see that since it's going down, we are all of 30 mils. We know that for certain. We also can see that we are all of 30.5, and I think even 30.6 on there. So we've got to go one more digit, and the easy way to do that is to take a sheet of white paper, just fold it in half, and put it underneath the liquid level, just kind of near the burette. And what that does is it bounces the light from the ceiling to the bottom of the meniscus, and we always read to the bottom of the meniscus. So here, this really illustrates that it's between 30.6 and 30.7. And so you have to estimate what that final digit is, and I'm going to call it, looks like it's just, oh, it might even be below 30.7. I think it is. So it's 30.7, and I'm going to say 3. It's about, it's not quite halfway between 0.7 and 0.8. So I'm going to say 30.73. On this one, the scaling is a little bit different because it goes by 2 mil increments that are marked 1 mil in between with the middle-sized hash marks. So 1 mil increments there. So 1 mil, and then there's only 5 divisions between each 1 mil increment. So that means it's going up by 0.2. So we can read this with certainty to the nearest 0.2, and then we must estimate the final digit, and so that's going to get us to a scale where it's really basically reading this to the same as the 50 mil burette, or 0.1 mil. So here it's clear that it's all of 58. I can see the meniscus is below the 58 mark, but it's not to 58.1 even. It's just past that. So I'm going to have to call it as best I can at 58.1.
All right, next we've got the different graduated cylinders. This one is the 250 milliliter graduated cylinder. And you can see that the labeled marks here, we've got a 60 and an 80, which means that halfway in between would be 70. And between 60 and 70, then there are only 5 delineations. And so each of these marks is worth 2 milliliters. And that means that you're estimating between two of the marks for that 1 milliliter place value, and that's as precise as you can get. So if we look here, again at the bottom of the meniscus, it's going to be 60, 62, 64, 66, 68, not quite to 70. So it would be 60, either 8 or 69, depending on where you estimate it to be. So 68 or 69 milliliters would both be valid measurements for this. You can mix them at the end.
Okay. Can I pick up the mix them at the end?
Yes. Next is some water that's in the 100 milliliter beaker. Here you can see the lines that are labeled 30 milliliters and 40 milliliters. And between the 30 and the 40, there are 10 delineations. And so that means that each one of these marks is worth 1 milliliter. And because it's a 1 at that place value, we would estimate 1 place further to the 10th place for any measurement with this. So we've got 30, 31, 32, 33, not quite to the 34. And so you would estimate where that is for your 10th place. So it would be 33 point whatever. Whatever you put for that last estimate is fine. I would probably go with 33.8 or 33.9 for this one. Next up is the 25 milliliter graduated cylinder. You can see the two marks here. We've got 10 milliliters and 15 milliliters. And there are 10 marks in between. So that means each mark is worth 0.5 milliliters. So we can tell, like, there are marks for every 1 milliliter. And so because each of these last marks is 0.5 though, we cannot go past that place value for estimating. So it's going to be to the 10th place on this. So we would go from 10, 10.5, 11, not quite to 11.5. So we might say 11.4 or 11.5, whichever you think it's closer to. And last, we're going to use the 10 milliliter graduated cylinder. On here you can see we've got marks for 6 and a mark for 8 with 10 markings between those two, which means that each of these marks is 0.2 or 0.2 of a milliliter. Because it's not 1/10, we cannot go 1 place further. We're going to have to stay at the 10th place for the most precision we can get. So if we look, this would be 7 in between. So 7.2, 7.4, 7.6. And it looks like it's right on that line. So you could make a valid measurement and say 7.5, but it really does look closer to 7.6. All right, next up we've got a set of beakers. In this one, this is a 600 milliliter beaker. We've got markings here that are labeled for each 100. We've got markings in between for 50 to help you estimate. The hundreds place is going to be known. The tens place is what's going to be estimated. So for this, you know that the hundreds place is going to be a 2 because it's not quite to 300 yet. And you would estimate whether you think that the next value, the tens place, should be 1, 2, 3, or 4. It wouldn't make sense to have it be 5 unless it was really close to the 5. It definitely wouldn't make sense for it to be a 6, 7, 8, or a 9. So I'm going to go with 240 milliliters. If you said 245 milliliters, that is too much detail. It has to be 240 milliliters or 250 milliliters. Next, we've got a 250 milliliter beaker. Here we've got markings for 50, 100, 150, 200, with markings in between for 25 milliliters between them. So again, like the flask, it's going to be the hundreds place is known, the tens place is estimated, and there will be a placeholder 0. For this, it's definitely in the 100 range because it's not up to 200. It's definitely less than 150, and we could go with 120 or 130 would be the best measurements on this. 120 or 130 milliliters. The last beaker we have today is a 100 milliliter beaker. There are smaller ones, but we're going to end with these. And here you've got marks for 20. This would be 30. This 40, 50, 60. And so there are marks for every 10 milliliters, which means that you can estimate to one place value further, the ones place. So it's definitely between 50 and 60, and so our known digit at the tens place is going to be a 5. And then you would estimate where this is, whether it's 53, 54, 55, 56, all would be valid. So I'll go with 54 milliliters. All right, so next up, we're going to do a couple of Erlenmeyer flasks. With these, they're not really meant for measuring with precision because there are not a lot of markings. You have one for 100, one for 200, which means that this is just going to be for 50. So because this is not, we have delineations for every one at the hundreds place, but not at the tens place. And so that means our tens place is what's estimated. And so we know that it's over 100, we know that it's over 200, we know that it's over 300, but not quite to 4. So our first known digit is the hundreds place, and it's going to be a 3, that it's 300 and something. This is going to be estimated, and so you need to think, is it going to be closer to 310, 320, 330, 40, 50? It actually looks like it's pretty close to just being 300, not even to 310. And this is more difficult than I anticipated it would be, because this one, to show one known digit and one estimated digit and one placeholder, is going to have to be written in scientific notation. Instead of writing 300, it would have to be 3.0 times 10 to the 2 milliliters. Our next flask, we can see the measurements for 50, 100, 150. So this would be 175. And again, so we have the known place value at the hundreds, but there are not lines enough for every one place value at the tens. And so the tens place is going to be what's estimated again. We know that it's definitely in the 100 range for the hundreds place. So the first known digit is going to be 1. And then your estimated digit is going to be wherever you think this is. So it's going to be more than 5, but less than 8. So it's going to either be 150, 160, or 170 milliliters for your estimate. I would probably go with 160 milliliters. So that's a 1 in the hundreds place for known, and then a 6 for the tens place that's estimated. So, all right, next we're going to show you how to use a beam balance. These are quadruple beam balance because there are 4 different beams. And the first thing that you need to make sure to do when you're using this is make sure that when there's nothing on the balance that it reads 0. This one does not read 0, it's not balanced. The line here is not lined up with the line here like it needs to be when all of these are at 0. So if this doesn't adjust to 0, if it's not zeroed out, the way to adjust it is by using this knob here, twisting it one way or the other, and you can see twisting it in is going to bring these closer together. All right, so now we can see that the line here and here are lined up, and that means it's zeroed out. We're going to put our object that we're going to measure, and there are a number of ways to do this. I think the most efficient and effective way is to start with the largest slider, and you see these have to be in the notches for them to actually be at that correct mark. And so when I move this over to the 100 mark, it's showing that it's too heavy. And so it is definitely not 100 grams. Starting with the tens place, I'm going to start out here. And again, making sure that the sliders are in the groove. So because it's too heavy here, but too light here, I know that I'm going to be doing this and then adjusting the smaller sliders further. So we can see here that using the 5 at the ones place is just a little bit too heavy. And that using the 4 is quite a bit too light. So our last slider doesn't have grooves, and we're going to start here and very gently tap it back. All right, so now we've got this balanced. It's time to get our value by looking at the sliders positions. So like I showed before, in the hundreds place is 0. In the tens place would be 9. In the ones place is 4. And each of these markings here is 1/10 of a gram. And so the tenths place is going to be that it's 0.9. There are 10 smaller markings between each of these tenths places. And so each of these small marks is a 100ths place. And so this is 0.91, 0.92, 0.93, 0.94. And because it had markings for every 100th of a gram, we can even go one place further for an estimate. And so it looks like it's just past the line for the 0.94. So we would say 0.941 or 0.942. If it were right on the line, you would still say 0.940. So for a final measurement, we have 94.941 grams for this figurine. So for a lot of these, we're measuring volume of liquids. We're going to look at how to measure the length, width, height, or physical dimensions of things. For that, we have two different tools. We can use a ruler, or we can use calipers. Because of this opening here, these are called vernier calipers. This is a vernier scale. If we look first at the ruler, you can see that each of these marks here is a centimeter, and the smallest marks, it says, are millimeters, and there are 10 between here, and so from 0 to 1, there are 10 millimeters in 1 centimeter, and that means that each of these marks is 0.1 centimeters, and any measurement made would go one place value further to the hundredths place, 2 decimal places. And you would just line it up as best as you can. And something like this, when you get close to it, now you can see on this piece of metal that the ones place is definitely going to be a 7. It's greater than 7 centimeters, but less than 8, so it's definitely going to be a 7. That's a known digit. You can also see that the leading edge of this piece of metal is in between the 7.5 centimeter mark and the 7.6 centimeter mark. And so that means that that also is going to be a known digit. It's going to be 7.5. And then we go one digit further for an estimated digit, and that could be 7.58 or 7.57 or 7.59 centimeters. It could also be 75.9 millimeters. Now in this photograph, I'm showing the difficulty when you're trying to measure the diameter of a round object, or really any irregularly shaped object. It's really difficult to know if you're really getting the diameter of something with a ruler, and so you use something called calipers instead to pinch the thing that you are measuring. In this photograph, I've used a set of vernier calipers to pinch the cylinder. You can see it on the far left, how it's being pinched in the calipers. And the way that you read this, you can see that first there's the 1 centimeter mark and the 2 centimeter mark. And you're going to use this first line as your reference for that place value. And so we definitely know that it's greater than 1 centimeter, but less than 2 centimeters in diameter. So the ones place is going to be a known digit, and it's going to, you can see that this is the 0.1, 0.2, 0.3. And you can see when you look that it's not quite to 0.3, but it is greater than 0.2. And so the tenths place is going to be 0.2. So it's 1.2, and now we've got to estimate. We could just estimate that it's very close. That we could say 0.29, but that's what the vernier scale is for. You see that there are 10 marks on this side of the window, and you're looking for which one of those looks like it's directly across from a line on the main scale. And to me, it looks like it could actually be the 8th line here. And so the estimated digit, the 100ths place, would be an 8. So we go with 1.28 centimeters for the diameter of this piece of metal.
Here's an analytical balance. There's one in each of the 2 chemistry rooms, and you'll be using these frequently over the course of the semester or term. These are precision instruments. They're very expensive, and we need to show you how to use these. So the setup on this is that it has a shield over the balance pan, and that's to protect the balance pan from wind currents. And that's because the pressure, the air pressure in the room, affects the mass of an object or the weight of the object. And I'll show you what I mean. If you look very closely at the scale, you can see that it is registering exactly 0. That may not be the case when you come up to the balance, especially if somebody teared an object. So let me show you what I mean by that. I'm going to briefly put this object on the scale. It'll measure. Now I can zero this out if I had a beaker that I wanted to add something to, but I didn't want to have to worry about the mass of the beaker itself, and I only wanted to think about what was being put in it. I could put the beaker on. In this case, I put a cork on, and all I need to do is hit this OT button, and it takes out whatever object is on the balance pan at the time you press that button. So now if I pull this off, it's going to show what the mass of that cork was, because it was at perfectly 0 when I put it on originally. So if you come up to the balance and you see a tear is on the balance, and you don't want that tear because you've got a different object that you're putting on there, you might have to zero the balance out. And you do that just by, again, hitting the OT button, and it resets it to 0. So the shroud over the top acts as a windscreen, and the reason why is that I'm going to just wave my hand over the balance and look at how the scale changes. So the pressure in the room and any air current in the room can affect the mass of the object. This is particularly true for hot objects. You can't put hot objects on the balance because the air is heated above that object, and the pressure is lighter above that object. So usually hot objects weigh less if you mass them hot than they would otherwise weigh if they were cooled to room temperature. So when you look at this, I'm going to put the object on. I'm going to close the shroud, so you can see I closed it, so there's no air in there. And now I've got a mass on here. What I know for certain is that it's all of 10 grams. I know that it's 10.9 for sure, 10.94, and what is uncertain or estimated is the very last digit. So even for an electronic balance, that 7 is an estimated digit. The chip that's in the balance has an algorithm that it uses, and it estimates there's many digits beyond that that have been measured, but they scale it back to a level of precision, in this case to the nearest thousandths of a gram. So even for the balance, the electronic balance, that 7 is an estimated digit. So for this, we know it's all of 10.94 with an estimated digit of 10.947, or the 7 1,000ths of a gram, and that's what you would record for the mass of this particular object.
So thanks for watching. I think that's enough measuring for today. When you come into class, you're going to be practicing using those same tools and measuring different amounts of liquids or different objects.